Today we are going to start Chapter 7.5, Part 2, and this is continuing our section with roots and zeros. Starting with Descartes' Rule of Signs, who was a very smart mathematician way back in the day, and he came up with this rule that helped you decide how many real zeros, positive zeros, and how many real negative zeros you would get in a polynomial. Okay, since we are starting to solve for roots and zeros given these polynomials with degree that are more than 2, any helpful hints that we can get along the way to steer us into the right direction to find those roots is great. So this is going to be one way to help us decide which roots we're going to be looking for, whether they're positive or negative. Okay, so Descartes came up with this rule, and he says if p of x is a polynomial with real coefficients whose terms are arranged in descending degree. Okay, so in order for this rule to work, first of all we need real coefficients, which if it's a polynomial, then we're good, because a requirement to be a polynomial is that it has real coefficients. So it has to have real coefficients, and it has to be in descending degree from the first to the last term. You don't have to have the place fillers like you have to do when you do synthetic division, how we have to put the zeros in to keep a spot. You don't have to do that for his rule, but you do have to be going from biggest to smallest degree throughout your polynomial. Okay, so you have to make sure both of those things are happening before you use the sign, before you use his rule. Okay? Then this is what happens. So if both of those things happen, then the number of positive, we'll read the green first. This is for positive and negative, but this is actually two phrases. So we're going to go through with positive, and then we'll go through with negative. So the number of positive real zeros of y equals p to the x is the same as the number of changes in sign of the coefficients of the terms of p of x, or is less than this number by an even number. Okay, so if you're looking at the polynomial, you're going to count how many times it changes sign, going from positive to negative or negative to positive. The number of times it does that, it is either, so say it does that 4 times, say you change 4 times, then you have at most 4 positive roots, okay? Or is less than this number by an even number. So then we're going to start subtracting 2. So you can either have 4 real roots, real positive roots, minus 2, so you can have 2, or you can have 0. So if you find 4 sign changes, then you're going to have 4, 2, or 0 possible roots. If you have 3 sign changes, then you're going to have 3 minus an even number, which would be 2, so you're going to have 3 or 1. Or if you have 2, you're going to have 2 or 0. If you have 0, you're going to have 0. Okay? So that's with positive roots. Negative roots, it's going to be the same concept. However, to find the initial number that you're going to start with, you have to plug in negative x and simplify. Okay? We're going to walk through a couple of examples. This is very wordy. The process itself is actually a lot simpler than what this is making it out to be. Okay, so make sure this is in your notes, and we'll move on to application of Descartes' rule. Okay, so I want to state the number of possible positive real zeros, negative real zeros, and imaginary zeros of this polynomial. Okay? So we're going to be using Descartes' rule of signs as well as the fundamental theorem of algebra, which is what we learned in part 1 of this section, which it should be in your notes. Okay. State the number of possible real zeros. I just thought of some extra credit. So if you're watching this video and actually listening to my words and watching the whole video, I want you to show me in your notes in class, at the beginning of class, your fundamental theorem of algebra, and then Descartes' rule of signs. I want to see it written out in your notes, and that will be extra credit. Okay? So here we go. We have this polynomial, and so we're going to use Descartes' rule of signs. So he says if we're going to find possible number of positive roots, okay, notice we're not finding the roots itself, but we're finding the possible number of them that there are. Okay? We want to look for sign changes of the original polynomial. So here, this coefficient is what? This is a 1, which is positive. So if this is positive, this is a negative 6. Going here, this is a negative 3, so that's negative. A positive 7. -8, and a +1. So we want to count how many times the sign changes. So going from positive to negative, that is one sign change. Check. Going from negative to negative, that is not a sign change, so that doesn't count. Going from a negative to a positive, that is a sign change, so that counts. Going from positive to a negative, that is a sign change. And going from a negative to a positive, that is a sign change. So how many sign changes do we have? We have 4. Which means that we're either going to have 4 real zeros, or descending by an even number, we're going to have 4 or 2 or 0. We can't have any negative roots, so we stop at 0. Okay, so the number of possible positive real zeros is 4 or 2 or 0. Okay? Now, to find possible negative roots, it says that we have to find the number of sign changes in P of -x. Okay, now we learned back in section 1 or 3, I forget which one, that whenever this is replacing x, we go wherever we see an x and substitute this in. So here, I'm going to have a -x to the 5th, -6 times a -x to the 4th, -3 times a -x to the 3rd, plus 7 times a -x squared, -8 times -x, plus 1. Whew, almost ran out of room. Okay, and now we want to simplify. Okay, so we're going to use order of operations, which order of operations is exponents first, and then you multiply. So here we have a -x to the 5th power, which is -x times -x times -x times -x times -x. So we're going to get an x to the 5th. Is this going to be positive or negative? Negative times negative is positive, times negative is negative, times negative is positive, times negative is negative. So a -x parentheses to the 5th simplifies to a -x to the 5th. Okay? Here we have a -x to the 4th, which is -x times -x times -x times -x. We want to do this part first. Order of operations, we simplify this first and then multiply by the -6 out in front. So this is going to give us an x to the 4th, -1 times negative times negative times negative gives us positive. So we're going to have a positive x to the 4th times this -6. So that coefficient stays a negative. Here we have a -x to the 3rd, -x times -x times -x. That's going to be a -x cubed. It's done. So a negative times a negative makes this a positive 3x cubed. Okay, this guy simplified to a -x cubed. Out front we have it multiplied by this -3. So that becomes a positive 3x cubed. Over here we have a -x squared. -x times -x, that gives us a positive x squared. So a positive times a positive, that's going to stay. And here we have a -8 times a -x, which is positive 8x, and then plus 1. Okay? Now that we have simplified that, now we want to look through for the sign changes. So here we're going from a negative to a negative, to a positive, to a positive, to a positive, to a positive. So that is not a sign change. Negative to positive is positive to positive, positive to positive, positive to positive. So here we only have one sign change. So possible negative roots is 1. Okay? Now, using our fundamental theorem of algebra, we want to figure out how many possible imaginary roots we're going to have. Okay? So, using our fundamental theorem of algebra, this is to the power of 5, which means I'm going to have 5 roots total. Okay? So, if I have a total of 5 roots, okay, I have 3 options for positive and 1 option for negative. So I know with negative, I'm going to have 1 for sure. With positive, I can either have 4 or 2 or 0. So we need to figure out possible number of imaginary. Okay? If I have 4 positive and 1 negative roots, that gives me 5 total roots already. Since 5 is my total, that would give me 0 imaginary roots. If I have 2 positive roots and 1 negative root, that's 3 total roots, which means I have 2 left over, so then I would have to have 2 imaginary. Or, if I have 0 positive roots, 1 negative root, that means I have to have 4 imaginary in order to make it for a total of 5. Okay, so possible positive, negative, we have to have 1 possible imaginary. Done. Okay, let's do another example. Alright, we're going to do the same thing, I just didn't write out the directions for this one. Okay, so if we're looking for possible positive, we want to look for sign changes. This is positive, negative, positive, positive, negative. I am in descending order, which is why I did that right away, but you want to make sure that you're descending in degree before you use Descartes' rule of signs. So positive to negative, that's a sign change. Negative to positive, positive to positive, positive to negative. So here I have 1, 2, 3 sign changes. So that means I have 3 or 1 positive roots. Okay? With the negative, I want to calculate my p of negative x, which means I have 2 times negative x to the 4th minus a negative x cubed plus 5 negative x squared plus 3 times negative x minus 9. Okay? Negative x to the 4th is going to be a positive x to the 4th times a 2. That will just stay positive x to the 4th. Here I have a negative x cubed, or negative x cubed, which if you multiply that, the result of this will be a negative x cubed times that negative out in front, which means I'm going to be adding an x cubed. I have negative x squared, which this is going to give me a positive x squared, times that 5 means that it stays the same, positive 5x squared. And then I have 3 times the negative x, which is negative 3x, minus 9. So looking for sign changes, positive 2 to a positive x cubed is no sign change. Positive to a positive, positive to a negative, negative to a negative. So here again, I have 1 with a negative. Okay, so if I have my positive real, my negative real, I also need to figure out my imaginary for a total of, if I have how many total roots am I going to have? The degree of the polynomial. So here I'm going to have 4 total roots. Okay? With positive, I'm going to have 3 or 1. Negative, I know for sure I'm going to have 1. Okay, so here if I have 3 positive and 1 negative, that means I already have 4 roots, so I don't need any imaginary. Here if I have 1 positive and 1 negative, that means I'm going to have 2 imaginary to make up the difference. Okay, keep in mind, in this imaginary column, they're going to have to be an even number, because imaginary numbers come in pairs, which are the conjugates. Okay, so if you have a 1 or a 3 sitting in your imaginary column, you did something wrong, because imaginary numbers always come in pairs. Those are the conjugates. Okay? That is the end of section 7.5. I'll see you in class.